You know that feeling, right? When you're trying to get something just perfect. Maybe you play guitar and you're tweaking those little pegs, just trying to hit the right pitch. Or maybe you're baking, trying a new recipe, adding a bit more flour, maybe less sugar, and it doesn't quite land. It's that cycle, isn't it? Trial and error. Kind of just guessing, hoping you stumble on the best way. It can be, well, pretty frustrating. Welcome to the deep dive. Today, we're looking at a way to cut through all that guesswork. We're exploring a really powerful, systematic way to find the best solutions, something that goes way beyond just intuition. We're diving into design of experiments, or DOE. And our mission here for you is to give you a kind of shortcut, to show how you can really optimize things by understanding how different factors play together, finding those aha moments where it all clicks and you get where you want to go just faster. Okay, so to make this real, let's imagine something. Let's go back to, say, ancient Rome. Picture yourself on a military engineering team. You've got this big catapult, your X Pult, let's call it, but there's a problem. It keeps missing the target, this crucial 2.5-meter mark. And, there have even been some, let's say, friendly fire incidents.
Not great.
So the general, he's given you a very clear order. Hit that 2.5-meter target consistently.
Yeah.
Every time. This X Pult scenario, that's going to be our example as we explore DOE. So, okay, let's start right there. Why? Why bother with structured experiments like this? What's the real problem that just, launching a few rocks and tweaking things can't solve?
That's really the heart of it, isn't it? And there are four main reasons why we turn to structured experiments. It's not just about being organized, it's strategic. First, it's plain old problem solving. Our Roman engineers, their catapult isn't hitting the mark. So DOE helps them systematically figure out how to improve that response, how to get it closer to 2.5 meters. Second, it's about optimizing. This goes a bit further, not just hitting the target, but maybe achieving the best possible distance really consistently, or maybe doing it with the least amount of strain on the catapult. In business, you might think of highest yield or, fewest customer complaints. Third is robustness. This is crucial. It means making sure you get that same result, that 2.5 meters, even if things aren't perfect, even if the type of rock varies a little or there's a bit of wind, making your process tough, resilient to small changes. And finally, number 4 is screening. Often, especially early on, you might have tons of ideas about what could be affecting your catapult. DOE helps you efficiently sort through all those possibilities and find the vital few, the factors, the X's that truly make the biggest difference. So you focus your energy where it counts.
Okay, those are really solid reasons. Problem solving, optimizing, robustness, screening, makes sense. But if we're going to design an experiment, there must be a model, right? A way to think about all the pieces.
Absolutely. We have a basic model. Think of it like this. You've got your controllable inputs. These are the knobs you can turn, the things you can deliberately change. We call them X1, X2, X3, things like that. Then you have uncontrollable inputs, or noise. These are things that might mess with your results, but you can't easily control them. Maybe the temperature that day, or slight differences in materials, let's call them Z1, Z2, Z3. All these inputs, controllable and uncontrollable, feed into your process. For us, that's launching the catapult. And out of that process come your quality characteristics or outputs. These are the results you measure, Y1, Y2. So for the X Pult, that's the distance the rock travels, maybe also the consistency of the shots.
That model seems clear. Inputs, process, outputs, with noise thrown in. But could you give us maybe a more modern example, just to see how it applies outside of ancient warfare?
Sure thing. Let's take semiconductor manufacturing. Molding. Specifically, it's a high-tech process. Your controllable inputs there could be things like the exact type of material used, the transfer pressure during molding, the heater plate temp, the mold temperature, even things like which mold type is used or the specific operator running the machine. Very precise controls. And the outputs, the Ys, they'd be things like package strength, or their cracks, is everything aligned, or encapsulation quality, or their voids, is the surface rough, are there blisters. You can see how tiny changes in those inputs could really impact the final product quality.
Okay, that really brings it home. Very different context, same core idea. Now, thinking about how people usually approach problems like this, especially before they know about DOE, what are the typical starting points? Because I'm guessing it's not usually this structured.
No, you're absolutely right. Most people, and probably our Roman engineers initially, they'd start with one of two things: simple trial and error, or maybe something slightly more organized called one variable at a time, or OVAT. Trial and error is, well, it's pretty much what it sounds like. Our engineers might just start launching 20 shots, maybe. They'd fiddle with the angle here, pull back a bit harder there, try a different rock, just hoping they hit 2.5 meters. They might keep a tally, sure, but there's no real system. It's kind of random, chaotic even. And like you said, potentially leading to some unfortunate misses. OVAT, one variable at a time, is a bit more structured. They think, okay, let's figure out how one thing affects the distance.
Mm-hmm.
So they might do a series of shots just changing the number of rubber bands, keeping everything else the same. Then they reset, and maybe they test different launch angles, keeping the rubber bands and everything else constant. And the pullback angle, and so on. Maybe 10 shots for each setting to see how accurate it is.
Right, OVAT feels more methodical. But what's the catch? If our engineers are trying to consistently hit 2.5 meters, what are these approaches missing?
They're missing something huge. Interactions. Real-world things are complex. Changing the rubber bands might help on its own. Changing the angle might help on its own. But what happens when you change both at the same time? Does the effect just add up? Or does changing the angle work differently depending on how many rubber bands you have? That's an interaction. Trial and error completely misses this. OVAT misses it too, because you're only looking at one thing at a time. You never see how factors influence each other. And without understanding those interactions, you can't really find the true sweet spot, the truly optimal settings. You might find something that works okay, but it's probably not the best it could be.
Okay, so if trial and error is like fumbling in the dark and OVAT is maybe like using a dim flashlight, how do we turn on the stadium lights? How do we see everything, including those tricky interactions?
That brings us to full factorial design of experiments. This is where we get really systematic. Instead of one factor at a time, we look at every possible combination of the factors we're interested in at different levels. And usually, the most common starting point is a two-level design. It gives you a ton of information pretty efficiently. The notation we use is 2K. K is just the number of factors you're testing. So if you have 3 factors, it's 2 to the power is 3, which means 8 runs, 8 different combinations you need to test.
2 levels, so you mean like a high setting and a low setting for each factor?
Exactly. So for our X Pult, we define our factors, our main effects, and pick 2 levels for each. For example, number of rubber bands. Level 1 could be 1 band low. Level 2 could be 3 bands high. Launch angle. Maybe level 1 is 0 degrees. Level 2 is 75 degrees. Pullback angle. Level 1 at 20 degrees. Level 2 at 120. Ball type. Maybe level 1 is a ball with holes. Level 2 is a solid one. And the key is we test every combination of these high and low settings. The huge advantage of full factorial, you get it all. You learn about the main effect of each factor on its own. You learn about all the interactions, how pairs of factors work together, even how 3 factors may interact. And critically, you can actually quantify the relationship. You can build a mathematical model like YFX that describes how the inputs x's predict the output, y or distance.
Whoa, a mathematical model? So you could predict the distance even for settings you didn't explicitly test?
Precisely. That model is incredibly powerful. It lets you understand the trade-offs. Maybe hitting 2.5 meters perfectly requires settings that really strain the catapult. The model helps you find a balance. Maybe hitting 2.45 meters very consistently with much less strain is actually better. You can optimize for multiple things at once. That's a massive advantage.
Okay, that sounds amazing. A predictive model. But I'm thinking if you have, say, 6 factors, 2 to the power of 6 is 64 runs. That's a lot of catapult launches. Seems like it could get really time-consuming and maybe expensive. Is there a downside to testing everything?
You've nailed the main limitation. As K, the number of factors, goes up, 2K grows incredibly fast. 6 factors, 64 runs, 7's 128. It gets big. And here's the thing. While 2-factor interactions are often important, interactions between 3, 4, or more factors are usually, well, pretty small or non-existent in most real systems. So a full factorial design, especially with many factors, might spend a lot of your resources, your time, your materials, your degrees of freedom, which is like your experiment's information budget, estimating these tiny, complex interactions that don't really matter much. It's not always the most efficient use of effort.
Right, using up your experimental budget on things that probably aren't significant. So, okay, if we are doing a full factorial, maybe with fewer factors, how do you keep track of all those combinations? 16 runs for 4 factors. How do you make sure you run them all correctly?
Good question. We need structure. We use something called Yates standard order. It's a systematic way to list out all the combinations. We use a simple code for the low level of factor, plus Banter for the high level. Let's take that 4-factor example, 16 runs. Factors A, B, C, D. For factor A, the first column, you'd list 8 minuses, then 8 pluses. Simple. For factor B, second column, you alternate. 4 minuses, the 4 pluses, the repeat 4 minuses, 4 pluses. Factor C, 2 minuses, 2 pluses, repeat it all the way down. And factor D, just alternate minus, plus, for all 16 rows. This pattern guarantees you cover every unique combination systematically. And importantly, this specific order has nice statistical properties that help balance the design, making the analysis cleaner later on.
Okay, Yates' order gives us the plan. But just having the plan isn't enough, right? We need to make sure the data we collect during those runs is actually reliable. How do we protect ourselves from weird variations or mistakes during the actual launching?
Excellent point. Execution matters just as much as design. We need data integrity. And there are 4 key techniques we use: repeats, replicates, randomization, and blocking. First, repeats. This is simple. For any one specific combination of settings in your experiment, like 1 rubber band, 0 degrees angle, 20 degrees pullback holy ball, you might launch the catapult multiple times, say 4 times, without changing anything. This helps you understand the short-term variability, like how much does the distance vary just from shot to shot with the exact same setup. It gives you a better average for that specific run. So for a 4-run DOE, you might do 4 repeats per run and use the average distance. Next, replicates. This is different. A replicate means running the entire experiment, all 16 combinations in our example again, maybe on a different day or with a different crew. Doing replicates increases your overall sample size. It makes your conclusions much stronger and helps you be more confident that the effects you're seeing are real, not just random chance. You might do the whole 16-run experiment, say, 3 times. That's 3 replicates. Then there's randomization. This one is absolutely critical. Don't just run the combinations in the nice, neat Yates order, 1, 2, 3, 16. Instead, you randomly shuffle the order in which you perform those 16 runs. Why? Because things might change over the course of the experiment. Maybe the catapult parts wear slightly, maybe the weather changes, maybe the operators get tired. If you run in a fixed order, those time-based changes could get mixed up with the effect of your factors. Randomizing spreads that risk out, protecting your results from hidden biases.
So you don't accidentally think the catapult shot further on run 16 because of the settings, when really it was just because the sun came out.
Exactly. Randomization protects against those lurking variables. And finally, blocking. This is a smart strategy when you know about a potential source of variation you can't control, but you can group your runs by it. For instance, maybe you have 2 different teams of engineers running the catapult, one on the day shift, one on the night shift. You could block by shift. You run half your experiment randomized within the block during the day, and the other half also randomized at night. This prevents differences between the shifts from messing up your analysis of the main factors, rubber bands, angles, etc. And as a bonus, you can often estimate the effect of the block itself, like, does the night shift consistently shoot shorter?
Okay, wow. Repeats, replicates, randomization, blocking. This is serious stuff. Our Roman engineers are becoming real scientists now. So let's picture simulation 3. Our team, they're armed with this knowledge. They generate their Yates order for the full factorial design. They'd carefully plan in repeats, maybe 3 launches per setting. Replicates, let's say they run the whole thing twice. And crucially, they'd randomize their run order for each replicate. They'd have a clear data sheet. They run the experiment, collect all the distance measurements. Then they use a DOE statistics tool. Maybe even back then they had clever ways with abacuses, but today we'd use software. They analyze the results, identify which factors and interactions significantly affect the distance, and figure out the settings that should get them closest to 2.5 meters consistently. Finally, they take those optimized settings, fire 10 confirmation shots, and see how well they hit the target. That's a world away from just guessing. That full factorial approach feels incredibly thorough. You learned so much. But back to that issue of scale. What if you have lots of factors, say 8, 10, 12 things you suspect might influence the catapult? A full factorial gets huge, like hundreds or thousands of runs. Is there a way to be more efficient?
Yes, absolutely. That's a very common situation in real-world problems. And it leads us directly to fractional factorial designs. We already touched on this. Those high-order interactions, 3-way, 4-way, etc., are often tiny. Running a massive full factorial just to measure them might not be worth it. So fractional factorial designs let you run only a fraction, like half, or a quarter, or an eighth of the full factorial combinations. The big benefits: economy, fewer resources needed, speed, you get results much faster. It makes experiments with many factors feasible. But there's always a trade-off. The price you pay for that efficiency is that you lose the ability to estimate some interactions clearly, and you need a bit more know-how to set them up and interpret them correctly. We use the notation 2kp. K is factors, P tells you the fraction size, P1 is a half fraction, 2k1 runs, P2 is a quarter fraction, 2k2 runs. We also talk about resolution, denoted by R. Understanding the trade-offs here is really key. The main concept is confounding, sometimes called aliasing. In a fractional design, because you're not running all combinations, some effects get tangled up. You might have a situation where the effect of factor A looks identical in the data to the interaction between factor B and factor C. They're confounded. If your analysis shows that this combined effect is significant, you can't tell for sure if it's really factor A causing it, or the BC interaction, or maybe both. They travel together in your limited set of runs. You can often spot this by looking at the design matrix
if the column of pluses and minuses for factor A is identical to the column you'd get by multiplying the B and C columns. They're confounded.
Ah, okay. So you save runs, but you get this ambiguity. How do you manage that? Is there a way to control how things get confounded?
Yes, that's where resolution comes in. It's a number, typically Roman numerals 3, 4, or V, that tells you about the pattern of confounding in your chosen fractional design. Higher resolution is generally better, meaning less problematic confounding. A resolution 3 design is the most economical fewest runs. But main effects, like factor A, are confounded with two-factor interactions, like BC. This is risky, because if a two-factor interaction is important, you might mistakenly think it's just a main effect. A resolution 4 design is better. Main effects are confounded with three-factor interactions, less likely to be significant, but two-factor interactions might be confounded with other two-factor interactions. Still some ambiguity, but main effects are cleaner. A resolution V design is even better. Main effects are confounded only with four-factor interactions, very unlikely, and two-factor interactions are only confounded with three-factor interactions. This gives you much clearer results for your main effects and your important two-factor interactions, but it requires more runs than resolution 3 or few. So choosing the resolution is a strategic decision. How many runs can you afford versus how much clarity do you need about specific effects and interactions?
Got it. So it's a calculated risk, balancing efficiency against clarity. Our Roman engineers, they're now operating at a whole new level of sophistication. So how would they put this fractional approach into practice? Okay, simulation 4. The engineers, now masters of efficiency, decide they have maybe 6 factors but can't afford 64 runs. They choose a fractional factorial design, maybe a 2-6-2, which is 16 runs a quarter fraction. They'd carefully select a resolution 4 or V design, understanding the confounding pattern. They generate the Yates order for that specific fraction. They still incorporate repeats, replicates, and randomization. Those principles always apply. They run their linear experiment. Then, using their stats tool, they analyze the results, keeping the confounding in mind. Okay, this effect is significant, but it's aliased with these other interactions. Based on our engineering knowledge, it's most likely factor X. They pinpoint the likely optimum settings, and finally, the 10 confirmation shots to verify their accuracy. They've potentially reached the same conclusion as the full factorial, but with maybe only a quarter of the effort. That's smart experimenting.
Exactly. And it's important to stress, these aren't just abstract ideas. There are practical tools to help. We mentioned the X Pult tally checklist. Get things like a SIPOC map that stands for suppliers, inputs, process, outputs, customers. It's a great way to map out your process at a high level before you start experimenting, making sure you understand the boundaries and key elements. There are also specific design of experiment planning templates, tools for stakeholder analysis, who needs to be involved, dedicated data collection templates formatted for DOE, and of course the DOE Excel statistic packs or other software that handle the complex calculations for analysis. These tools make DOE much more manageable in practice.
What a journey, seriously, from just kind of guessing with trial and error through the slightly more organized OV, then hitting the big time with full factorial designs where you see everything. And finally, learning how to be clever and efficient with fractional factorials when things get complex. It really shows how DOE lets you zero in on the best settings, build those powerful predictive models, and truly understand what makes a process tick, whether it's our catapult, that semiconductor line, or really anything else.
And that really brings it back to you, the listener. How can you use this? We used catapults in manufacturing, sure, but these DOE principles, they're universal. Anytime you want to improve something, optimize an outcome, understand cause and effect, DOE thinking can help. Optimizing a business process, a marketing campaign, perfecting that sourdough recipe, getting more out of your workouts, even figuring out the best way you learn something new. The core ideas are the same. Identify what you can change, your factors, decide on levels, high-low. Plan a systematic way to test combinations, collect good data, analyze it to see what really matters.
So, here's something to think about. Is there a process in your life right now that you mostly handle with trial and error? Could be anything: brewing coffee, managing your emails, maybe even planning your commute. What might happen if you applied just a couple of these DOE ideas? Maybe just identify 2 or 3 key inputs, pick a high and low level for each, and try just the 4 or 8 combinations systematically. How much faster could you find what works best for you? And how much more confident would you be that you could repeat that success? It sort of reframes the world, doesn't it? Not just random stuff happening, but a series of experiments just waiting for you to optimize them.